Our next programming concept is on threads in computer programming. The first part of this tutorial will focus on the idea of threads at a high level, not before moving on to what they are and how they work within Android itself. But first, some history. Computers, before 2005, could only do one thing at once. Let me explain. It wasn't until 2005 existed, so all computers only had one CPU, one core, one brain, if you like. And as there was also no technology around hyperthreading or any way to split the single CPU, the single core, this meant, quite literally, that it could only process one thing at once. There you can see the example of the types of computers we had in the late 90s and early noughties. Now, if you were to use a computer in the mid to late 90s, perhaps going on one of the early websites, watching a video, moving the mouse, switching between programs, you wouldn't have the impression that the computer was only doing one thing at once, as the technology then did allow the rapid switching between tasks, so fast in fact that you would almost not notice it, and you would think that multiple things were happening at once. But actually, there was just a long queue of tasks to be processed in order by the one CPU, the one core, and it was only through very, very fast switching between all of those tasks that it could give the impression of more than one thing happening at once. But it wasn't. The CPU could only process one task at once. The introduction of more than one CPU core allowed true multitasking. From 2005, when the first dual-core processor hit the scenes, this is when one computer could do two things at once. Literally. One task could be processing in one CPU core, and then another task could be happening in the other CPU core at exactly the same time, in parallel. Indeed, this very idea is called parallelism, which is a slightly tricky word to say, but this means two things happening at the same time, two bits of code running at once in the two different cores. And then, as we know later on, CPUs had more and more cores, quad-core computers or even octa-core computers are quite common these days. But not only that, there's been certain technologies introduced that allowed the splitting of a single core into multiple processes, into multiple threads, a term that we'll cover in just a moment. And this big evolution in the way that computers process commands and instructions has enabled our software to be very, very efficient, has enabled the user experience to be more and more smooth, free of interruption. And the whole idea of multitasking and doing more than one thing at once is crucial to our understanding of threads. So, what is a thread? A thread is a sequence of commands that can be executed independently of other code. If we take, for example, our Android programming in Java or Kotlin, we understand that we type these commands, these instructions, in a relatively human-readable language like Java or machine code, more like ones and zeros. But fundamentally, these instructions are reading from top to bottom. They're reading in a certain order. And if you have only one thread and only one core, well, then our entire program is running sequentially in a sequence. And if any one command were to take quite a bit of time, like to go away and fetch a rather large download, well, in a single thread, in a single sequence of commands, you would have delay while waiting for that particular command to complete. And that could then interrupt the user experience. So a thread is the ability to gather up a sequence of commands, a separate flow of code, and that can be ran independently or even at the same time as other threads, as other code. So then you're not blocking the other code from running. And this is very, very powerful. You can think of the idea of life before threads and life after threads by relating it to roads. If you only have one thread for your entire application, then you're only allowing a single lane of traffic, with each car representing a single command. If you get a particularly slow-moving command, like a big lorry that might represent you downloading something that takes a long time to fetch, you're going to be blocking all of the other commands behind it, forcing the user to wait. It's quite inefficient. With multiple threads, you can think of this as multiple rows that can run in parallel or at the same time as each other. If we take the top row with a single yellow line as the main thread for our program, well then the other row can represent background threads. Maybe we would have another thread performing a sequence of commands to do some image manipulation, like upscaling or downscaling an image, or compressing some video, or anything else that might take quite a long time. Multiple threads allow a sequence of commands, some code, to run independently and even at the same time as other code, which is fantastic. In fact, the idea of threads is so fantastic that it was introduced in the concept of processors. Threads allow a single CPU to run more than one task at once, or even a single CPU core. There's technologies like hyperthreading that came about not long after multiple cores were introduced, and this essentially shares a single CPU, a single processor core, amongst multiple threads. It effectively allows us to run multiple streams of code, multiple sequences of commands at the same time, even within one CPU core. So hopefully you can see how this is an incredibly powerful idea in being able to move long-running complex code into its own environment, its own thread, that can run at the same time as other code. This can be known as concurrency, where the word concurrent literally means existing at the same time. Concurrency, more than one thing happening at once, without depending on each other. So, how does this relate to us? Well, Android supports multi-threading. This comes part and parcel of the system that Android runs on, and it's not very difficult to achieve. Something important to know, however. When your app launches from the system, a thread is created, and this is known as your main thread. And this is very important because if something goes wrong with your app that causes a crash or there's a big delay, well, you're not going to block the whole Android phone. You're still going to be able to switch tasks. The music you might be playing in the background will still play. So immediately when your app launches, it's in its own environment, if you like, its own thread. And this is known as the main thread for your app. And this main thread, which is also known as the UI thread, is responsible for everything that happens on the screen. And this is straight from the Android documentation. Responding to user input, changing the display with some new text, changing the colors, having a button click event. This must all happen on the main thread. That's mandatory. The system requires it. And so, we, therefore, must ensure that the main thread is never blocked. And this brings us nicely back to the problem we discovered in the previous tutorial. Accessing the database is a potentially time-consuming thing. As it happens, the SQLite database is incredibly fast, but it's still a non-trivial amount of time as far as the Android system is concerned. However, if we need the main thread to handle all the things to do with the display, like the user interface, responding to user touch, well, we can't do anything that takes any significant amount of time on the main thread. As doing that is going to block the user from touching the phone, or make it appear like it's stuttering, or that things aren't swiping or moving or updating as they should do. And so, because of this, when it comes to time-consuming operations like our database, what we need to do in Android is perform these time-consuming operations in a different thread, in the background, running it at the same time, but in its own environment, so the main thread is free to continue working uninterrupted. Unfortunately for us, there are a number of ways we can go about doing this in Android, and some of them are really quite simple. So let's go straight back to the project now and look at moving our database operations to their own thread. Returning now to Android Studio, we got up to the point of trying to create a task, or trying to get all tasks from our database, and running into a crash. Looking at the error in the logcat, we can see it was caused by an illegal state exception, cannot access database on the main thread, since it may potentially lock the UI for a small code. Click that, you'll be fine. It caused this. To overcome this, it's going to come from current means, or who have maybe should be the best way for Kotlin. Spoiler alert, the best way in Kotlin for concurrency, for thread management, is with a thing called coroutines. And coroutines are absolutely fantastic. However, there's quite a bit of learning around that to really understand what's going on with coroutines. and we will be moving towards that. And a firm understanding of threads, and also with running code in background threads, this understanding is going to really help when we move on to coroutines. So for this tutorial, we're going to simply launch a new thread and run our database operations on there. Later on, we'll look to upgrade this to using full Kotlin coroutines. But for now, above the create task line, so there's a few ways you can do this in Java. I'm going to show you by far the most simple way. The way you would do that is with, first of all, a new object called thread. And you can see this comes from the java.lang. So this is a Java thing. And then we'll do the curly brackets to make our new object. Now there's lots of different constructors for this thread object. We're going to take the top one that says target runnable. And in very, very simple terms, this runnable is going to be simply a block of code that we can run. So we have our thread. I'll put that in some space. And above it, we'll create this runnable. Now a runnable is a simple interface with one method that says run. So what we'll do is we'll go ahead and create an anonymous class above this thread that implements the runnable interface. And that's the slightly strange syntax of object, then colon, and then the runnable interface. No class constructor brackets because it's just an interface. So we'll do the curly brackets. And then we have an error which says we must implement the members. And when I select that, I can see there's just one method, and that method is called run. So when I press OK, we have our code block for the run method that we need to implement. So if I delete the to-do, we can move these two database operations inside that. So I'm going to cut those two lines and paste them inside the run block. Ignore the suggestion for now to convert to a Lambda. We'll be doing that in just a moment. In fact, we'll be doing a couple of simplifications of the code. I just wanted to show you it in its entirety so you can see what's going on. So we have implemented the interface runnable, providing the run method code, and we can assign this to a variable. So we'll call this simply our runnable with a lowercase r. And now we can pass this runnable inside the thread. And what's going to happen is when the thread starts, well, it's holding on to our runnable. It has this runnable object that we've passed in, and it will know when the thread starts to call the runnable's run method. Simple as that. We've covered callbacks before, we've covered interfaces before. This run is some callback code. So the thread's going to hold onto our runnable, and at the appropriate moment, it's going to call the runnable's run method, a callback, as there's quite a bit of setup the thread needs to do first under the hood before it's ready to run that code. And then that's pretty much all we need to do. There's just one final command. We need to call .start on the thread. And believe it or not, that's all we're going to need to do to run these two database operations in the background. Don't worry if right now this seems a bit cumbersome, quite a lot of code. We'll be using a couple of Kotlin tricks to simplify this. So when we run this, how can we tell if it's been successful? Well, if you remember, in our device file explorer, in the data folder, scrolling down for me to com.vinnorman, at the moment we don't have a databases folder. Once the database is successfully created, the Room library will put the database files in our databases folder. And we learned that the way the Room library works, it will only create the database files and tables once the first database operation completes. It couldn't complete before because we were trying to run it on the main thread, but now with this code here, we're creating a runnable, some code to run in our thread, and then we're starting our thread. So this code will complete successfully, and all being well, we will see a databases folder here once we start the app and then refresh the folders. So let's go ahead now and do exactly that. I'll click run. I'll just load up the emulator. This time I am successfully inside the app, so it hasn't crashed this time. And if I scroll down, click on my com.vinnorman.getitdone folder and click the refresh icon, I can see we now have a databases folder. And when I open it up, there's a few files there, get it done database. So we know that our database has created and this code did complete successfully. Let's clean up this code a little bit. If you look at this suggestion on line 40, if I do Alt Enter, Option Enter, it says we can convert it to a Lambda. This is a single interface with one method. And quite conveniently, if you have a Java interface with just one method, Kotlin allows you to convert it to a Lambda. So we'll do that. So we can see now we have this runnable and then a Lambda. That's a little bit cleaner. So then we could actually, rather than having a separate runnable variable, we could copy just this runnable Lambda like this. So I'll cut that and delete that. And I could just paste that in there directly. That's okay. But now I'm being told that the runnable declaration is redundant. This thread constructor knows that if you get a code block, it's going to be a runnable. So we can use that warning to remove that. Then we're getting another warning which says the Lambda argument should be moved outside of the normal brackets. So we will do that. So Alt Enter, Option Enter, move the Lambda outside of those brackets. So maybe that looks a little bit better. We have thread. We then have our runnable Lambda in the normal curly brackets, followed by dot start. So already this is a lot cleaner. However, we can go one step further. Kotlin has a useful function, which is thread with a lowercase t. We've seen things like this before with our shared preferences editor, if you remember, the .edit function. So if you do thread with a lowercase t and select this one with the curly brackets and make a few line breaks, well, inside this function, if I just command click into it, you can see it has a default argument of starting equals true. It will start automatically. We don't need to call .start. It happens under the hood. So actually we can just put our runnable code block inside this thread with a lowercase t, delete the previous one, and that's all we need to do. So in Kotlin, launching a background thread, giving it some code, and then having that thread automatically start is very easy. Let's give this a different task name. This can be another task. And we'll run this again just to confirm we get no crash. Okay, so all is fine. So this is a very simple way of launching a background thread in Kotlin. Now please note there are multiple ways you can achieve this in Java. Another one that you may have seen or you may encounter is the idea of this executors.new single thread executor. So there's this syntax here, and you can call .execute. That has a useful little curly bracket lambda, and we could also put our code inside there. Okay, that's also another way of doing it. For our purpose, we don't need this. However, the single thread executor has some more power, some more control. You can do things like delay when it starts, or run multiple tasks, multiple code blocks, or even cancel it. So when you Google background threading in Android, you may see this as well. It's important to understand there are multiple ways you can achieve putting code on a background thread. For us, using this simple thread function in Kotlin is going to be absolutely fine. Just thought I'd show you that one. So there you go. With a very simple block of code there, that thread block with the curly brackets, we can very easily run some code in a separate thread, which is exactly what we need for our database operations. So another nice thing we could do is we could use the getAllTasks command, and we could use that to show how many tasks we have. It could be nice to have a little toast that says how many tasks we have in our database. So let's go ahead and try and do this inside this thread. So we'll do toast.makeText. Context is this for this activity, and we'll say number of tasks, then a colon. Now we need a reference to our all tasks result, so we'll make a local variable called tasks. Okay, so the number of tasks equals $tasks.size, and we'll do toast.lengthlong.show, and we'll try and run this now, and we'll see what happens. Okay, it appears that our app has crashed. So if we head into Logcat, and we can see main activity line 46 is where the crash occurred. That's our toast. And then we have a very strange looking error, null pointer exception, can't toast on a thread that is not called looper.prepare. Now, if you were to Google this and search on places like Stack Overflow, eventually you would find that what we're trying to do here is we're trying to do a UI action. And remember, showing a toast is very much a user interface thing. We're updating the display. Well, we're trying to do this on a thread that is not the main thread. It is not the UI thread. The main thread and the UI thread is the same thing. So now we have a problem. We're inside this background thread, but we want to update the UI. We want to display something. And later on, we're going to want to actually show all of our tasks. So we're going to need to get the data from a background thread and show it on the UI thread, on the main thread. So how can we do that? Well, you may think one way of doing it is actually cutting this line and just pasting it outside of the thread, but that's not going to work. We don't have access to the tasks variable. The code in this thread block is going to be running in a separate thread in parallel, concurrently at the same time. It's probable, or even likely, that this line 48 for me, my toast, is going to happen before even the thread has got to the getAllTasks command. And now we're running into one of the many problems with concurrency. This code and this code will be happening at the same time, and there's no guarantee as to which will happen first. So we can't do this, so I'm going to cut this line and put it back inside the thread. So what we actually need to do inside this thread is communicate that we now want to run the code back on the main thread, on the UI thread. And fortunately for us, there's a very easy way of doing this. There's a function that simply says, with a lowercase r, run on UI thread with another curly code block. And what this will do is, it will send a message from inside this thread saying, hello main thread, or UI thread, same thing. I have some code that I'd like you to run on the main thread, please, when you get a chance. We're kind of sending a message to post some code to the main thread, and then when the main thread is able to receive that, it will run the code. So it kind of takes care of being in one thread and then moving to another thread for us. So we can simply run this code inside this block here that says run on UI thread. And because the run on UI thread block is within the thread, we do have access to the tasks variable. So I'll remove the line breaks, tidy this up a little bit. I'll remove the line break between those two commands. So we open a background thread. We then perform our database operations. We create a task. We then get all tasks. And then once we've performed the database operations that we need to be on a background thread for, we can then return to our main thread, the UI thread, with this run on UI thread code block that takes care of all the complexity of doing that for us. We'll already have 2 tasks in our database, so we'll do a third task. And so we're expecting when we run the app, there to be no crash, to see a toast that says number of tasks, and hopefully there will be 3 tasks, as this line will have completed successfully 3 times by the time we run this again. So let's go ahead and run the app one final time. Okay, we have a number of tasks 4, so probably somewhere in my previous examples, I ended up running that 1 extra time. Okay, it doesn't really matter. I can run it again, and we expect it to say 5. Yep, so we can see that the create task command is working properly, and indeed we can see that the get all tasks command also worked. So I'll just close down the Device Explorer and the run pane for now, and focusing on these lines of code here, we are able to quite easily create a new thread and put some code that will run in this thread, which can run at the same time as the main thread, the UI thread. And once we've done our database operations, all of the hard work, we're able to quite easily get back to the UI thread to update our display, to update our UI. This isn't the most efficient way of doing things. For example, if you had a very, very, very long running thread created like this, and then you were to quit your app, well, there's no lifecycle management with this. There's no attachment to our activity on destroy or anything like that. And so that code would continue to run, which is not ideal. In the future, we will move to Kotlin coroutines, and these coroutines, which are just a very lightweight thread, but also much more powerful in the way that we can use them, well, these can attach to the lifecycle of our app, which makes things much more efficient. And it's also quite a bit easier than this. This is still quite a few lines of code. Okay, but congratulations, you've created your first background thread, you ran your database operations on this background thread, and then you successfully posted the results of those database operations back to the main thread, to the UI thread, where you've been able to display the result of get all tasks. In the next tutorial, we'll have a quick look at the database inspector to see how we can very easily see what's inside our database, and then we can really get to work with the functionality of our app now, as our database is fully working, and we're able to quickly and easily perform operations on it using this thread, which is fantastic.